Good morning, welcome to new lecture. Today I will solve several problems using stiffness method and force method, and we will look at several problem nature. We should understand the concept and we will see how we can approach to this kind of problem. We should first understand the concept of the problem statement. Then after digesting the problem statement, it will be easy to solve it. Let's see, we have one inclined ceiling. We attach 3 bars to this ceiling. These bars, they have different lengths, and we attach to one rigid beam. So, Young modulus for each one it is E. It means material property is the same. For example, all of them we made using A36 steel. Cross-sectional area for the first bar it is A. For the second bar it is 1.5 A. For the third one it is 2A. So the cross-sectional area is different. You see, it gets bigger. Length for the first one it is L, for the second one it is 1.5 L, and for the third one it is 2L. Again, length is different. Spacing here from bar 1 to bar 2, it is again L. From 2 to the 3, it is L. This rigid beam is subjected to one external load. External load magnitude is P. Pay attention, external load magnitude is P. It means it is known value. Young modulus E, known value, can be any number. Cross-sectional area, these are known, length is known value. Unknown, the location of external load, the location of X. We want to find X in a way so that after applying this external load, after deformation, this beam, this rigid beam, remain horizontal or level. In the initial location, before we apply external load, you see it is horizontal, it is level. Then I apply external load, I pull down. After deformation, I wanna remain horizontal. So where I should apply this external load? What is the location of external load from point 1? It is unknown X. I should find that. How I will find that? Let's look at problem behavior one more time. We have rigid beam here, external load P, the location of external load from point 1 it is X, it is unknown, but I know we have one bar here, another bar here. The spacing between bars is L and L. Let's look at the stiffness of each bar to see what is the stiffness of each bar. Axial stiffness is equal to Young modulus times cross-sectional area divided by length. So for this one, axial stiffness will be EA over L. For this one, axial stiffness will be, let's see, 1.5 EA over 1.5 L. For this one, axial stiffness will be 2EA over 2L. You see here 1.5 and 1.5, they will cancel each other. And 2 and 2, they will cancel each other. So axial stiffness for each one, it is EA over L. I can show with one constant number like K. So what I have here, now I have rigid beam. Assume I substitute this bar with equivalent spring. This spring behaves exactly like that bar with effective stiffness K. Space between these is L and L. I want to find the location of external load after deformation. This beam remain horizontal. It means each bar or spring, they should deform equally. Deformation for bar number 1 should be equal to deformation of bar number 2. That should be equal to deformation of bar number 3, or each one, delta 1, delta 2, delta 3 should be equal. In that case, this beam will move down only. So deformation in this one, if it is delta, this should be delta, this should be delta. If the stiffness times deformation will be force. So force in spring number 1, F1, force in spring number 2, F2, force in spring number 3 is F3. If I write summation of forces in vertical direction, equilibrium equation in vertical direction, what I have F1 plus F2 plus F3 minus P is equal to 0. Or I can write K delta instead of F1 plus K delta instead of F2 plus K delta instead of F3 is equal to P. From here, 3K delta will be equal to P. And from here I can write delta, K multiply delta should be equal P over 3. If I call this point, point 1, and if I write summation of moment respect to point 1 equal to 0, I will have F2 times L, F2 is K delta times L, plus F3 times 2L, so F3 again it is K delta times 2L, minus P times X, P times X should be equal to 0. From here I can write, if I add these together, I will have 3K delta L is equal to Px. Instead of K delta, from here I can plug P over 3. So 3 times P over 3 times L is equal to Px. 3 and 3, they will cancel each other. P will cancel from both sides. So X will be equal to the L. It means we should apply load exactly under bar 2 at midspan. Do you think it is reasonable answer or not? Yes, it is reasonable answer. Because appearance-wise, this structure, it is not symmetrical structure. But if you look at the stiffness, we put equivalent stiffness. They will be three springs, and these stiffness are identical. So the stiffness of spring are equals. So, and they will deform equally. So deformation in spring 1 is delta, spring 2 is delta, spring 3 is delta. So it is symmetrical system. In that case, X should be equal to the L, and we should apply force exactly at midspan. Or in other words, if I apply force in midspan, I pull down this rigid beam. This rigid beam will move down. That tilt angle or rotation angle will be equal to the 0. It will not rotate clockwise or counterclockwise. Only it will move down, and that deformation, we assume it is delta. So that is problem number 1. Let's look at another problem. We have, let's just consider we have one rigid beam. Okay, assume we have one rigid beam. We attach this rigid beam using 2 bars to the ceiling. And distance from here to here, it is 2 lowercase a. And from here to here, it is a. So I should modify the picture a little bit because I put in middle, which is not right. So I put, for example, here. Now maybe it is better. Okay. We apply external load P here. And Young modulus for each rod is E, cross-sectional area is A, length is L. Problem statement says find the ratio of F1 over F2. And this is rod number 1, this is rod number 2. F1, internal force in rod number 1. F2, it is internal force in rod number 2. We want to find this ratio. How we will find that ratio? Let's see what we have. We have one rigid beam. If I apply load here, I pull down. This rigid beam will rotate respect to support O. So it will rotate like this. It will deform under rod 1. Deformation, I assume it is delta 1. Here, deformation, it is delta 2. And here we have one rod, another rod. Spring or rod number 1 stiffness is EA over L. The stiffness of rod number 2, again it is EA over L. So, what will be the force F1? F1 will be, this is if this stiffness times delta 1. So, if I assume EA over L, one constant like K, F1 will be K delta 1, F2 here will be K delta 2 because the stiffness for both it is equal EA over L. Now from geometry, what is the ratio of delta 1 over delta 2? We know, look at to this triangle, the small one and big one. Delta 1 over delta 2, it is equal 2A over 3A. From here, delta 1 over delta 2 will be equal 2 over 3. So, F1 over F2 will be K delta 1 over K delta 2. K and K, they will cancel each other. Delta 1 over delta 2 is 2 over 3. So, ratio of F1 over F2 will be 2 over 3. Let's look at another problem. Assume we have two cylindrical bars. We have two cylindrical bars. Both material they have made from same material, so material properties is the same and length is the same. We have two rods. Cross-sectional area is cylindrical shape, for example. For the rod number 1, Young modulus it is E, cross-sectional area it is A, length is L. For rod number 2, Young modulus, it is E again. Cross-sectional area, it is smaller. It is A over 2. The length, again, it is L. So pay attention, E Young modulus, A cross-sectional area, L is length. All these parameters are known. We know this. And here everything is known too. So there is a small gap between these two rods. A small gap, the magnitude of that gap, it is delta. Delta, again, it is known value. For example, it is 1 millimeter. It is known value, a small gap. So there is no connection here initially. And we have two supports, and you see they are fixed supports. We apply load here. We pull this rod from left to right and this one from right to left. If we pull these both ends, we will have elongation. So that elongation finally will cover this delta, and we will attach these two ends together. So as soon I apply load a little bit, I have elongation in each one. I show with blue. And finally, both ends reach to each other. That elongation from both sides finally will cover that delta, and they will reach to each other. And we attach both ends together. We attach that. Now there is a connection over there. Now we will release this system. Initially, here there was no connection and it was gap. And internal force and stress inside of these rods, they were 0. Now we apply force, we'll pull out both sides and we attach to each other, then we release it. Now it is not stress-free. There is internal force and stress. First is the question. This internal force, it is tension or compression? It is evident this internal force should be tension because we have elongation in each one. And tension will produce elongation. So definitely force inside it is tension force. So then what is the magnitude of this force? Because after we attaching, if in connection we have force, unknown force like F, this F will transfer in this rod and this rod. So internal force in rod number 1 and rod number 2, it should be equal. And that internal force will transfer to this support and this support, even support traction, it should be equal. Now, what is the magnitude of that F? In order to find magnitude of the F, we should look at the behavior of this structure. This force F is effective to rod 1 and rod 2. If I apply force to the rod 1, so force divided by stiffness of rod 1, we will have elongation in rod 1. We will find the magnitude of deformation in rod 1. Plus the same force divided by stiffness of rod 2, we will have deformation of rod 2. Both deformation, if we add together, find it should cover delta. It means it should be equal to delta. So I can write force divided by stiffness of rod 1, which is EA over L plus force divided by stiffness of rod 2, which is EA divided by 2L, should be equal to delta. Delta is initial gap, which is known. From here, we have one equation, one unknown. We can find F. F should be equal to E A delta divided by 3L. Young modulus, it is known. A cross-sectional area, it is known. Delta is initial gap, it is known. 3L is length, is known. So we can find internal force in this system. Internal force F divided by cross-sectional area here, we will have stress in rod number 1. Internal force F divided by cross-sectional area here, which is smaller A over 2, we will find stress in rod number 2. That is another problem. Let's look at another type problem. Please, first, once I'm explaining the problem statement, try to take notes. Then, don't look at my solution. Think about that. See, you can understand. You can solve by yourself. Then, watch the solution. See your solution is right or wrong. If it is right, no problem. You will watch one more time. You will understand better. If it is wrong, you should understand what was your mistake and you should correct yourself. If you watch these videos continuously, problem statement, then my solution, in that case, you will not able to develop that skill in your brain. You will not think like engineer. Assume we have one cone. We have one object, it is cone-shaped object. This object is made of linear elastic material. So the material is linear elastic. Young modulus, it is E, which is known. Unit weight is gamma. I know the unit weight is gamma. And the cross-sectional area at base, it is A naught. The height is H. This cone is sitting on the table, assume we put on one table, on safe weight. The only external load we have, it is self-weight. It is gravity load. It is self-weight. Find the deformation of the tip point, point O, under self-weight. Find deformation of the tip, point O, under self-weight. It is clear, point O will move a little bit down. It will come, for example, point O prime because of self-weight. Find that delta O. How much is that? So, you see here cross-sectional area, it is not constant. In all problem we solved up to now, it was constant. Here cross-sectional area is not constant. Look at to the formula we had. We had deformation is equal external load times length divided by EA. Here external load force, it varies. From tip to base it varies. From tip to base it is increasing. So it is not constant number, it is function. And A, again, it is not constant number, it varies from 0 to A naught. So how I can find deformation, how I can find deformation will be integration of, because force it varies function of the location x. Instead of L, I will have differential length dx divided by E AX. AX cross-sectional area. In any location we are cutting and we are drawing free body diagram. Assume from point O, I move down. How much I will move down? X. I cut here and I assume this is dx. This is small differential length, I assume it is dx. Cross-sectional area, I assume here it is AX. Now, what I have force. Force here will be weight of this part. Weight of this part from tip up to here. Weight of this part. How much is that weight? Volume times unit weight. Volume times unit weight will be weight. So weight is equal to volume times unit weight. Volume from tip up to here, it will be equal to cross-sectional area here, which is AX, times the height, it is X, divided by 3. That will be volume of this green part, green cone, times unit weight, gamma, will be weight of this part I'm cutting. Okay, that weight apply force for differential length dx. So I can write, instead of fx, a and this x over 3 times gamma times dx, okay, divided by E, cross-sectional area for this cut point, for this differential element length, again it is AX. If I integrate this from x values from 0 to entire height h, I will find delta. From here you see AX and AX, they will cancel each other. And after that I can write integration from 0 to h, gamma x dx over 3e. If I do this integration, delta will be equal to gamma h squared over 6e. Because gamma unit weight of the material, unit weight for any material, it is known value. We know the gamma. Cone height is known. Young bunches for material is known. We can find delta deformation under self weight. Okay. Let's look at to another problem. Assume we have one cylindrical shaped bar, cross-sectional area is circular, so it is cylindrical bar. One end is free, another end is fixed support. This is subjected to non-uniform axial distributed load. So non-uniform axial distributed load. What does that mean? Axial load at tip it is close to 0, then from free end to the support magnitude is increasing like this. So the magnitude is increasing from free end to the fixed support. It is distributed in entire length and it is non-uniform because each one you see, it gets from fixed support to free end, it gets smaller and smaller. The variation is, if I draw here, variation is like one triangle. At the tip it is 0, at the support it reaches to the maximum value, which is I show with Q naught. Q and this 0 Q naught. So it is function of x We measure x from free end, so it is function of x. This non-uniform axial distributed load Qx is equal to Q naught x over L. At free end, x is equal to 0. If I plug 0, external load here is 0. At support, x is equal to the L. If I put L instead of x, L and L, they will cancel each other, and the external load will be Q naught. What is the deformation of this rod under this non-uniform axial load? This is problem. In order to find that, I will cut in x distance and I will assume one small element. This small element length is differential length is dx. What is axial force effective on this element? If I cut here, I'm cutting here. What is axial, resultant axial force from here to here? Axial force at free end, it is 0. Axial force here, it is in the x distance, Q naught x over L. So from 0, it reached to the Q naught x over L. What is the resultant axial force? Resultant axial force will be area underneath of this triangle. So resultant axial force will be Q naught x over L times height times x times 1 over 2. Area underneath of this triangle will be Q naught x squared over 2L. Now, this axial force is effective on this element, so dx will be equal to integration of fx dx over EA. X varies from 0 to L. Entire length it is L, and cross-sectional area it is A, and Young modulus it is E. So it will be integration from 0 to L. Instead of fx, we will plug from here Q naught x squared over 2L times dx over EA. After we integrate this term, we will end up with Q naught L squared over 6EA. Finally, deformation delta, deformation for this rod will be equal to Q naught, intensity, maximum intensity of this axial load times L squared length divided by 6EA. Let's look at another problem. Assume we have rigid beam. This rigid beam here, we attach to the wall, and at midpoint there is one inclined rod. Again here we attach to this hinge support, and it is horizontal initially. I apply force, external force P here. Length from here to here it is L over 2. From here to here it is L over 2. This is a rigid beam, so we neglect the deformation of this beam. Young modulus for this rod, it is E. Cross-sectional area, it is A. Length is L. This angle is 60 degrees. This is point A, point B, point C. Problem statement tells us calculate delta C deformation at point C. Initially, this is horizontal level. After that, we apply external load P at point C. So how this beam will deform? It will rotate respect to point A, and we will have elongation in this rod. It comes like this. What is delta C? Calculate this. Try to calculate it. Next session, I will start from here. Thank you so much for watching this lecture. See you next session.